Let's look at how the right-hand rule determines the direction of a vector cross product, specifically A cross B. We begin with two vectors, A and B, shown with their tails together at a common point. This shared origin makes it easier to reason about the direction of the cross product. Because vectors A and B lie in the same plane, their cross product must point perpendicular to that plane. First, bring your flattened hand and point it along the direction of vector A. The order matters here. This is A cross B, so we start with A. Without moving your hand from that starting point, rotate it so that your index finger stays aligned with A while your palm turns towards vector B. Now let your middle, ring, and pinky fingers curl naturally in the direction of B. Reversing this order would reverse the final direction of the cross product. Extend your thumbs. Your thumb points perpendicular to the plane containing A and B. This thumb direction gives the direction of A cross B, here labeled vector C. The right-hand rule helps determine the cross product direction only, not magnitude. As the perspective of this scene rotates, notice that A and B determine a plane while C points out of that plane. This highlights an important point. Cross products are inherently three-dimensional. Let's clear the scene and look at another example. Here's a new pair of vectors, again sharing a common origin but pointing in different directions. Once more, these two vectors define a plane. Start by aligning your flattened hand with vector A, reinforcing that A is the first vector in the cross product. Rotate your hand so that the index finger stays on A, and then curl the remaining fingers towards vector B. Extend your thumb to find the direction perpendicular to the plane. That thumb direction defines vector C, the result of A cross B. Viewing this from multiple angles again confirms the three-dimensional relationship between the two vectors and their cross product result.